So, in sort of a summary, if we want to do a line integral of any function f of x y dot ds on a path r of t equals x of ti plus y of tj, where t goes from a to b. Now the integral we did was on a closed path, but this doesn't necessarily have to be a closed path. Often, usually in fact, it won't be. Okay. To do this line integral, we start by partitioning our t interval. T goes from a to b, so we have a equals t naught, and t sub n equals b, and t1, t2, up through tn minus 1, completing the partition, where t sub I is just the t for the typical ith interval. And I'm not going to use the subscripts. I'm going to kind of bypass that so we can just concentrate on the main idea. I assume you know how to do Riemann sum and take its limit. Now I assume that, but I know it's not always true. Still, we're not going to address that here. Okay, so what do we do in a typical interval? Well, in a typical interval, you have f, you have a sample point t star, so you write down this. Okay, now your ds, we have a delta s, which is equal to some multiple of the unit tangent vector. Okay, this moves us in the direction of the path, and it moves us some displacement delta s. What's delta s? Well, delta s really depends on your delta t for your interval. Okay? So how do we get this? First of all, we evaluate our unit tangent vector. Well, first mistake. Our unit tangent vector is just going to be what? It's going to be the derivative of our r of t function, because of course r of t defines our curve. So it's going to be r prime evaluated at t star, and that's a tangent vector, but then we got to divide by the magnitude of r prime at t star. This gives us our unit tangent vector, so there's our t. And delta s is what? Delta s is how fast we're moving times our time interval. If you want to think of this in terms of time, whether you think in terms of it in terms of time or not, it's going to be this vector times our average velocity times delta t. Now you kind of have to prove that, and then you have to move away from the assumption that this is time and so forth. But whatever I mean by v bar, I mean the rate of change of r with respect to t. I multiply it by t, and I get the change in r. So that, excuse me, this is going to be our r prime at t star divided by the magnitude of r prime at t star, in other words our unit tangent vector again, multiplied by v, which is our r prime of t star, times delta t. Now, and it's not our prime of t star, it's actually our magnitude of r prime of t star multiplied by delta t. Okay? And of course that then just equals r prime of t star times delta t. Now we could just skip delta s equals this. Okay? We could skip the parts with the absolute value signs and all that. But you wouldn't understand. Okay, if you skip that, you're not going to understand what this means. Another thing this means is this is the rate of change of r with respect to t, whether t means time or not. And then we're multiplying by the change in t. If we take the rate of change of r with respect to t multiplied by delta t, we get the change in r. So one way or another, this is going to be the change in r. It's going to be the change in the magnitude of our change in r, and that's what this is. Divides out, gives us this. Okay, so we do that so that our f dot delta s is going to equal our f, again evaluated at x of t star, y of t star, dotted with our prime of t star multiplied by delta t. And I didn't draw that exactly where I wanted to, but hopefully you can read that. And then the sum of our f dot delta s approaches the integral from a to b, because we partitioned the interval from t equals a to t equals b, of f of x of t, y of t, dot r prime of t dt. So if we know the parameterization of our curve and our function f as a function of position in space, we get the line integral, which again represents the sum of, if you think in terms of the work analogy, or whether you do or not, it's the sum of the components of f in the direction of delta s multiplied by how far delta s is. Okay? Very important concept. You won't believe how important it is, and maybe by the end of the last chapter here, you still won't believe how important it is, but you'll find out. Okay, very good.